Wow, our senior year is flying by. We've just finished our last spring break, and here we go. We're coming down the home stretch. We've got 1 month to go, and certainly time to define ourselves and define the class of 2013 and leave a real strong legacy within our little calculus family here over the years. But tonight we're going to talk about series, and I think it's the easiest topic of the entire year, especially if you feel good about taking the limit as n approaches infinity, because that's the name of the game, and that's the only thing we're going to do tonight. But a couple of bullet points here. A sequence is a function whose domain is only the set of positive integers. Emphasis on integers, okay? So when we talk about n can be a 1, n can be a 2, a 3, so forth. N cannot be 1.5. Okay, it's only allowed to be positive integers. We got function values, a sub 1, a sub 2, a sub 3, a sub n. They're called the terms, and a sub n is called the nth term here. And basically what we're talking about, we're going to continue to answer the same question over and over again. Does the sequence converge or not? And we're basically asking ourselves, does a sub n get close to an actual finite number, or does a sub n approach infinity? That's basically the big difference here today. And so basically, this third bullet's the most important. The sequence is convergent if the limit simply exists. That's it. If the limit doesn't exist, then it's divergent. It's as simple as that. Let's clarify that third bullet one more time, just so we're all crystal clear on how easy this is tonight. So first of all, just notationally speaking, we're going to say a sub n represents the sequence that's being discussed or analyzed. Okay, here's how simple it is. If the limit as n approaches infinity for a sub n equals a finite number, in other words, it exists, okay, then we would say that a sub n converges. Otherwise, it diverges. And when I say otherwise, I mean the limit either doesn't exist because of oscillation, or it doesn't exist because it approaches infinity, positive or negative. So that's how simple it is. We're going to keep it really simple, and we're going to fly through a bunch of these examples super quick. All right, just for discussion purposes here, I've given you very similar problems. The one on the left here is a sequence, and the one on the right here is a series. And basically a sequence, just to remind you, is a list of numbers. Basically we're going a sub 1, comma, a sub 2, comma, a sub 3, Over here in the series, now we're going to talk about the sum of the numbers within that list. It's a cumulative sum, so and we're just adding them up as we go. So on this first one, here's how different it is. We'd say the limit as n approaches infinity for this particular sequence, power fight, and we've got same power on top as bottom. We compare the coefficients and we get 2. So we say, yeah, this one converges, no doubt about it. All right, therefore convergent. However, on the right side over here with the series, when we do that same limit and we get 2 for the answer, we would say, whoa, wait a minute, that's not equal to 0, so it instantly diverges according to the nth term test. So that's how we would handle them differently on a sequence versus a series. We're going to see how fast we can buzz through these several examples. Up here at the top, I've given you a few special sequences to think about. This first one I think is a no-brainer. We've got small over large. A natural log function is the snail or the turtle of all the math functions. It's smaller even than a linear function like n. And the other one here on the far right, again, that's small over large. We would say any polynomial, like x squared, x cubed, x to the fifth is smaller than n factorial. And then a couple here in the middle, I don't want you to worry about memorizing these two. I just want you to perhaps use them today as we go through these examples. They might come in handy once or twice. So here we go, real fast here. 1406. Starting right here, I would say that this particular sequence converges, and it converges to -1 because of my power fight, same over same, compare the coefficients. Next one here, moving down the column, I would say this one converges, and it converges to 0 because of small over large. On the third one, let's see what we got here. This first set of parentheses converges to 1/2 times this next one converges. Let's see, that term right there becomes a 0. 1 minus 0 is 1. So by the time I multiply them, I got a convergence series to 1/2. And down here, again, this term, 1 over n approaches 0, sine of pi over 2 is 1, so again it converges to 1. All right, switch colors here real quick. 1410, we definitely have small over large, so it converges to 0. 1411, I'm going to go down the page here just a whisker. I'm going to condense it and rewrite it as the natural log of n over n plus 1. Just a real subtle trick. Now as n gets huge, this turns into the natural log of 1, which equals 0. So I would say yes, this one converges to 0 as well. 1412, kind of a little rascal, but it follows the same property as this rule up here. Again, I don't want you to worry about it or memorize it, but we'd say it converges to 1. 1413, similar rule. We're rewrite this one as the n plus 4th root of the quantity n plus 4. That one's kind of a tough one to spit out, but either way, it follows that same rule, so it converges to 1. 1414 here. I'll tell you what, we used to say that factorials were the biggest rascals, but I think he's met his match here. And whenever you meet something you haven't seen before, try plugging in a really large number like 1 million. So we've got 1 million factorial over 1 million raised to the 1 millionth power. Now 1 million factorial is, a million times the next smaller number times the next smaller times the next smaller. So you continuously multiply by smaller integers. Whereas 1 million raised to the 1 millionth is you're continuously multiplying 1 million by itself. The numbers are not getting any smaller. So I would actually say this is small over large, believe it or not. So therefore it converges to 0. And our last column here, 1415, I would say this is large over small. So this is the first one of the day so far that diverged. I'm going to just totally skip 1416. I don't want you to worry about it. I don't want to throw any unnecessary information at you. 1417 here, 1 over n squared is approaching 0. 1 minus 0 is, of course, 1, and 1 raised to any power is 1. So we'd say that bear converges to 1. 1418, one of our favorite ones. We know that as n gets really huge, arctan approaches a height of pi over 2, so that one also converges. And the last one here, I want you to split this one up. Perhaps that helps. Factor out the n, and then split it up. So we got nth root of n times the nth root of n plus 1. The plus 1 is pretty irrelevant once n gets into the millions and beyond. So we've got two limits that both have a value of 1. 1 times 1 is 1, so it also converges. I wanted to throw some true-false ones at you, and this is certainly one of the AP's favorite topics. It seems so simple, doesn't it? True-false, what's the big deal? We saw that all the way through elementary school. But the way the AP tackles this, when they talk about, which one has to be true, which one could be true, which one could be false, they really challenge us to think in some abstract ways. So I wanted to run through a couple here with you and just deepen our knowledge and understanding of sequences. And so our first one, they said if all the terms in my sequence are greater than 0 and the nth term approaches some limit of L, then L itself is greater than 0. And I would say that's definitely true. And feel free to hit pause here at any point. If you want to run through these, I should have mentioned this before I started A. If you want to run through these and try to answer them on your own, that'd be even better. And then come back and see if we agree and if our logic's the same. Part B here, if each term in the sequence is greater than or equal to 0, and again, a sub n approaches some limit, then that limit is greater than or equal to 0. I said that was true as well. It's hard to imagine that each term being positive and yet you somehow approach a negative limit. I can't think of any example for that. C and D, I'm not going to spend too much time on. I don't want you to really worry about this concept of being bounded. It's not really on our curriculum, but I think it kind of makes sense that if a sub n is bounded, it kind of means it has like a floor and a ceiling, and the terms can bounce freely in between the lower and upper limit. Then it converges, and that's certainly true. D, if a sub n is not bounded, it actually doesn't necessarily mean it diverges, so that one was false. But I don't want you to worry about D per se. All right, here's a good one. If a sub n is decreasing, then it converges. I said that one was false because the terms could be decreasing all the way towards negative infinity, and therefore the limit wouldn't exist. F's almost the same with one strong stipulation. If a sub n is decreasing and yet all the terms are promised or guaranteed to be greater than 0, then it converges. And I would say that's definitely true. I'm picturing something like 1 over n. The terms are getting smaller, but yet they're staying positive all the way through, and it certainly converges in that case to 0 itself. G, if a sub n is neither increasing nor decreasing, then it diverges. I said that one was also false. I'm picturing, if the terms flatline, like every term in the series is 2, then we would certainly say that that sequence converges to 2, or whatever that flat line is at. And then H, if A sub n is positive for all values of n, then the alternating version of that sequence approaches a limit of 0. So I had to think about this one quite a bit. So let's start off. First of all, every term in that sequence is positive originally. Then what the alternating sequence does is it makes half of them negative. Okay, so you've got half positive, half negative, and the limit here is going to kind of split the difference in that alternating series. So I said that this one was true. I said the limit would equal 0. We've got half the terms above the x-axis, half below, and it kind of visualize something. Most alternating series, kind of behave in this sort of fashion, although this one's not guaranteed to necessarily do this, but I'm picturing one that kind of funnels right towards the x-axis and has a limit of 0. So hopefully you feel pretty good about sequences. Hopefully we had a good time with those 90 multiple choice questions. I hope our work is strong. We've checked our answers and we've posed some great what ifs questions. I'm really looking for some strong insight to kind of go further and deeper than you ever have before mathematically. So 1 month to go, and let's finish real strong.